You want to talk a little bit about your background?
Sure. I'm currently doing a postdoc at MIT CSAIL. I joined MIT like 2 years ago as a postdoc, but I work with Professor Stefan Yagoka.
Mm,
She also learned like a similar topic like machine learning, satisfied learning, graph neural network stuff. And before that, I did my PhD in Peking University in China.
mm,
I also do mostly machine learning, but actually it was in the School of Mathematical Sciences, and also did my bachelor degree there
mm,
in the same school and same department
mm.
for like 10 years. So
Wow.
that's part of the reason I want to move to MIT, to have a different flavor, to have a different environment. Yeah.
Awesome. Maybe tell us a little bit about how you first got interested in computer science.
Uh, yeah, actually, I'm not really sure. I'm very interested in computer science,
Yeah,
but
yeah,
at the time that actually machine learning becomes seen, it's more under the title of data science.
right.
I don't know if people still remember that, but actually it's
Yeah.
very popular in 2016 when I actually have to choose my, what's my major
Mm,
for my bachelor degree.
mm,
And then that was actually this new program they call data science program. That was the first year.
mm,
And okay, I think that's pretty fun. It actually unifies, lots of topics in mathematics, like applied math. You have the numerical stuff, and you also have the statistical stuff. You also learn a little bit about computer science. It been mixed the holidays from all these different
mm,
things. I think that's really cool. That actually how I just get into this world, and I found this really amazing. It's not really similar to the other ones that you're very
mm.
established in the math, like prime math and statistics. They have very mature things, but I think data science just taking off at that time, and
Mm,
I think it's just a wonderful thing to be part of this party. Yeah.
Awesome. And so I guess after doing your undergrad, where you studied data
Yep.
science and the School of Mathematics at Peking, which is obviously an
Yep.
incredible school, you chose to get a PhD in applied mathematics. What made you want to get a PhD as opposed to go to industry?
Why do I PhD?
And
Oh,
what?
I think at that time, it's not as hot as today.
Yeah,
I
yeah,
think,
yeah.
and I still like doing machine learning. I think at the time I started, I think the machine learning algorithm is very fun, and I just want to read more papers and doing more research on that. I
Yeah,
actually start not doing the topic I'm doing now because there's no LMs at that
yeah.
time. I was doing more like a Bayesian neural network. You have this aesthetic flavor of Bayesian models, and you
Mm-hmm.
have this very powerful neural network. People are trying to combine and get them together. Actually, I'm fascinated by this topic for quite some time, and
Mm-hmm.
I think this is something that actually driven me to this like PhD that I want to do something very interesting. I think even today, I'm not really
Yeah.
driven much by the industrial impact, but most by the, how interesting this idea,
Mm-hmm.
this
Yeah.
kind of thing. Yeah.
Yeah, awesome, awesome. So in terms of some of your research interests, now you're getting
Yep.
your postdoc at MIT, as you mentioned, and you've worked broadly on a lot of different topics, including like advancing ML principles and foundation models. And a lot of your
Hmm.
interests range from things like self-supervised learning and reasoning, long context learning, safety, so on and so
Hmm.
forth. If you had to like describe your research interests, like how would you sort of describe them?
Yeah, I would say just machine learning. I think
Mm,
I'm not really limited myself to, one area because I think
mm,
this would be crazy. Actually, you will limit to yourself to one
mm,
area at this time because it's actually changing a lot. You
mm,
have to update your understanding. But I think more about machine learning and
mm,
more about the core principle, the core methodologies of these models.
mm,
Like I think 3 years ago, maybe I was trying to do contrast learning. I think I
mm,
did a lot of work on that space because I
mm,
that time really believe this actually the most elegant, beautiful thing that you can learn from the data without any human supervision.
mm,
But then after some time, you actually realize there are some limitations in this, contrast learning approach. Then
mm,
actually, I try to look into okay, what's the fundamental things about next term prediction, and what's their, how powerful are they can learn and how powerful they can generate. What's the problem in this between? But I think it's more about uh, So what's the core methodology? I want it to be super, core and super simple.
Mm-hmm.
Like you should not really create a very fancy things, but actually people cannot really use that in practice. I think by, fashioning that into a very simple methodology actually can work on some, I think key elements in this space.
Mm-hmm.
Yeah.
Okay, awesome. So you also are now doing a postdoc at MIT, which is very exciting. Congratulations on
Hmm.
that. And you're working
Thanks.
with Stephanie Yegelka, as you mentioned. Maybe tell us
Mhm.
briefly why you chose to work with Stephanie, how her interests align with your interests.
Oh, I think definitely have a perfect line with my
Yeah.
interest at STEM I apply for a postdoc because
Mm-hmm.
I work on several topics. It's not very common for like I work on three like major domains at that
Mm-hmm.
time, like a
Yeah.
satisfied learning and some robust learning, several learning, and
Mm-hmm.
also some graph neural network, like a
Mm-hmm.
structural learning, learning from structured data. And I think it turns out like Stephanie also work on all of these three directions as well.
Mm-hmm.
I think during her tenure,
Mm-hmm.
so I think that was a perfect match for me. And I think their team had done an amazing job at especially the satisfied learning. I'm most interested in. I think it would just be fantastic to work with her. And it's 10 hours. She's a super uh, nice and super sportive advisor.
Mm-hmm.
And she gave me, I think total freedom to explore my own agenda and doing my own research. So
Mm-hmm.
actually, I have some time, try to understand what's the limitation of current assessment learning and how to I can actually explore some new direction during my postdoc. I think
Mm-hmm.
that's actually some many people would actually have to deal with, after their PhD because the
Mm-hmm.
topics have changed.
Mm-hmm.
I think also I have a, kind of hard time, like half a year or something, trying to find this navigation. And I think strategy is totally supportive through this whole journey. And I think I'm kind of, find my piece now actually looking into this new problem. I think it's also very exciting to work on.
Mm-hmm.
And I think all more interesting, I think you can actually bring a lot of, insights from your old, topic
Mm-hmm.
and to the new topic. And then you see the connections between us is very, very beautiful. Yeah.
Mm-hmm. Awesome. Awesome. Okay, so
Yep.
maybe we can start discussing some of your papers. So you've been
Yep.
very, very, very successful as a researcher. You have lots of really great papers. So maybe we can
Thanks.
start with one of your most recent papers that was given an oral award at ICML 2025. If I'm not mistaken, it's Beyond Matryoshka, Revisiting Sparse Coding for Adaptive Representation. Do you want to maybe give us a
Mhm.
brief summary overview on what the paper does, and then maybe we can dig a little bit deeper?
Oh, sure. This paper is the talk about, more about the large scale vector search. Actually, it's a fundamental element for many systems like Google search. Sometimes
Mm-hmm.
actually you have a sentence you embed into a, embedding like a vector, and
Mm-hmm.
then you search that through all internet. And the way you do search is sometimes typically just to convert all this paragraph into embeddings, and you
Mm-hmm.
do the similarity based search over all this huge amount of vector database,
Mm-hmm.
and that's what you do and power this models day to day. It also is also become very useful for this kind of generative AI
Mm-hmm.
era. Especially your model have to also search over a large database and to work with a large database in
Mm-hmm.
order to have some fact based generation. So when people developing system like RAG, is also underlying technique is also this search mechanism. But I think in certain scenario, you want this search to be super fast. For example,
Mm-hmm.
Google search or
Mm-hmm.
such a sort of very huge database. You actually want it to be real time. And but your vectors could be very long. So actually
Mm-hmm.
that limits your computation and the complexity here. So how people approach this problem previously actually is was the de facto things in OpenAI and Google is through something called Matryoshka embedding. It's a very
Mm-hmm.
beautiful name, but what it says is that it's, give a long embedding. What you can do is that you can truncate the embedding to shorter and shorter embeddings.
Mm-hmm.
And it's like a Matryoshka.
Mm-hmm.
And then you train all this, multi kind of layers of embeddings with, the multi objectives for this model. That
Mm-hmm.
after this multi objective training, your model are able to deal with this kind of, I can use short embedding during my inference time for my own, efficiency interests. It's
Mm-hmm.
very adaptive. It's very good.
Mm-hmm.
But the limitation that by making this embeddings very short,
Mm-hmm.
you're actually limiting your model's capability by huge amount of capability. Like for example, you shrink a 4K dimension to like a hundred dimension, that actually is 30 flows, more than like 40 flows of loss of embedded, expressive power of these repetitions.
Mm-hmm.
Actually, it performance can degrade this a lot,
Mm-hmm.
and so people actually never do something below, like let's say 64 dimension, because that will be almost useless.
Mm-hmm.
And so actually, it's not much you can do, because as long as you compress the repetition dimension, you lose the expressive power.
Mm-hmm.
So actually, how we approach this problem, how to make it efficient without so much sacrifice,
Mm-hmm.
is through a different methodology. We don't truncate that to be a short embedding,
Mm-hmm.
but we keep the embedding dimension, but we make it sparse.
Mm-hmm.
So they still have, let's say, 4K dimensions, but you actually only activate a few dimensions on this 4K dimension. Let's say you can activate only 32 dimensions on this. To have a very sparse vectors, there are a few good things about sparse vectors. Firstly, it's much more efficient to store, because you can store it in a sparse format like CS or CSC, that you saves hundreds of memory.
Mm-hmm.
A more exciting thing is that with this sparse vector, you can also do a retrieval, with only sparse vector multiplication
Mm-hmm.
or sparse matrix multiplication. So actually, the complexity also only depends on the active dimension of this sparse vector, not depend on the whole underlying dimension of these models.
Mm-hmm.
So that means that you can have an alternative way on shrinking this to very small compute. uh, you can shrink that to 42 dimensions, but we can also shrink that to 42 active dimensions. That give you the same theoretical computation complexity,
Mm-hmm.
but actually by making sparse, you can still retain the expressive power much better than the short embedding paradigm. So I think that's what actually interests this, the whole community about looking this, our methods that actually give us the kind of the oral presentation for this, but because actually introduce a new way to look at this problem.
Mm-hmm.
And by making actually sparse, we show that you can achieve significant amount of gains over the original short embedding, like Matryoshka kind of thing at like 32 dimensions.
Mm-hmm.
And I think with that, you can go even further. You can
Mm-hmm.
convert that to 16 dimensions, 8 dimensions, 4 dimensions. It still works pretty good.
Mm-hmm.
It can even beat some of the 62 dimensions by using short embedding. So that should give you a lot of those improvements there.
Mm-hmm.
I think that's what we're really excited about this technique, and I think it could potentially transform how people are doing this efficiency issues, and can power a lot of application by delivering like 100-fold of efficiency improvements.
Mm.
Yeah.
Yeah, awesome. So I know one of the things that you mentioned in your paper
Yep.
is that a lot of the existing acceleration techniques are very different. So, like for example, we have pruning, quantization, distillation, and a lot of these
Yep.
methods mostly target embedding generation, whereas
Yep.
your approach, contrastive sparse representation learning, helps with the post-processing stage. Maybe tell us a little
Yep.
bit more about how you came up with this technique, why you specifically chose to optimize the post-processing stage.
Yeah, so I think it's also kind of inspired by the limitation of the previous method, because
Mm-hmm.
they want as I said, what you need to do is you truncate your repetition to short embeddings,
Mm-hmm.
and they found that you cannot really achieve this without fine tuning the whole neural network.
Mm-hmm.
If you only fine tune it, add a couple of layers at the end, actually the performance is pretty bad.
Mm-hmm.
So you have to fine tune the full neural network and for quite a long time.
Mm-hmm.
Actually, a lot of startups actually are doing it in this space, trying to compress this better.
Yeah.
Yeah, so we actually don't think this kind of optimal solution, because we kind of believe in the Platonic repetition hypothesis, that you only need one underlying repetition to express this adaptive repetition. So we actually borrow some techniques from the sparse autoencoder technique from a very different literature. That literature is called mechanistic interpretability. It's very popular as well. To try to understand how neural network works. And we actually found that, okay, this parsing technique, they're not only very useful for interpretability, but they can also be a very powerful efficiency things by making the sparse. And so our own initial hypothesis may be because this thing can retain the original reputation so well, maybe we don't even need to fine tune the neural network.
Mm-hmm.
And actually, what we observe in practice.
Mm-hmm.
Yeah, so I think it just worked as charm.
Mm-hmm.
I think sometimes better than expected. So I think okay, and we want to keep it simple, right? Because
Mm-hmm.
sometimes you definitely don't want to fine tune. You want to take a state-of-the-art embedding, so
Mm-hmm.
open source models,
Mm-hmm.
and you just fine tuning one layer,
Mm-hmm.
basically with our model, on the existing reputation, frozen reputation, and then you get the state-of-the-art sparse embedding models.
Mm-hmm.
I think that's what people would actually want to use for their own applications.
Mm-hmm.
Yep.
Awesome. Do you want to tell us maybe a little bit more about how you went about, testing this through different experiments? So, in the paper, you
Mm-hmm.
talk about a bunch of different experiments that you ran for evaluation, including image, text, multimodal
Mm-hmm.
benchmarks. And across almost all of these benchmarks, we see this common trend, which is that your approach, this contrastive, sparse representation, is able to outperform the Matryoshka representation learning algorithm, in terms of both
Mm-hmm.
accuracy and retrieval speed. How did you go about like designing these experiments?
Oh, I think because this reputation, we want to be generic. When we think about this methodology,
Mm-hmm.
converting that to parsing that, we don't want to think that it's just, it's only for images, only
Yeah.
for text, only for multimodal. And people are actually using all these repetitions everywhere. For
Mm-hmm.
example, when you're building, vision language models,
Mm-hmm.
you take some, let's say, plate embeddings,
Mm-hmm.
and you plug that into your model, and you do a lot of things upon it. So I think why not we just to show this such a generic methodology can outperform all the areas. That's a pretty, I think, ambitious goal. I
Mm-hmm.
think so. I think the first author is really good student, actually an
Mm-hmm.
undergraduate,
Mm-hmm.
and a pretty amazing job
Mm-hmm.
actually. But we start with doing the image Ethernet because it's
Mm-hmm.
kind of the standard, and MROs also report their scores on that. So
Mm-hmm.
I think it's very good thing to start with, actually verify the methodology of this. And with a pretty promising result, and we try to integrate, to multimodal scenarios and text embedding scenarios. I think after we actually released this paper, I think more interest actually comes from the text embedding model because
Mm-hmm.
people are using this, RAG models with text embeddings every day. So actually, after this paper, we also tried to also further push the frontier of this faster to actually see some quite gains even over the current version of
Mm-hmm.
this model.
Mm-hmm.
Uh, yeah, so I think that's something that you don't probably expect from the beginning, but
Mm-hmm.
I think to actually prove something about this model, uh, actually you get something, yeah, bigger than you expected. Yeah.
Mm-hmm. Awesome. So maybe now we can switch gears to another paper that you
Yeah.
had that was also accepted. This one is accepted to iClear 2025, and it's titled "What is Wrong with Perplexity for Long Context Language Modeling?" Do you want to maybe
Mhm.
give us a brief overview of this paper?
Oh yeah, so that's also another very interesting topic. It's more about not about more not about the the efficiency thing, but
Yeah.
more about the model's capability.
Mm-hmm.
We know that existing LLMs they are super capable if they deal with not very long context. But if
Mm-hmm.
I put my entire repo into this model kind of struggles on
Mm-hmm.
understanding the details of every token
Mm-hmm.
kind of lose that in the middle. So there are a lot of techniques trying to deal with this issue, especially I think the recent DeepSeek have a
Mm-hmm.
paper called native sparse attention. They try
Mm-hmm.
to create a new transformer variant that the model can only attend to only specific areas of the context. So actually, you can save a lot of compute during inference, but the model
Mm-hmm.
can also kind of be more focused on the areas that really matters. So
Mm-hmm.
I think they are fantastic architectural gains. But this paper actually talks the different things. That whether these models are trained, very wisely, actually tailored down to this long content understanding. Currently, people still people do long context the same as short context.
Mm-hmm.
You still use next time prediction to train this model, but just with a very long context, a very long context. That's it. But people do observe that's not very good about this because people found that if even if your model have a lower complexity on your long context, meaning that your model is bad at next term prediction at your long context, which is your training objective, but it's not necessarily improve the perform at this long context benchmarks, like how I can retrieve the things from my uh, huge, long context. People design the benchmarks and have the training perplexity or validation perplexity. They don't correlate. The
Mm-hmm.
correlation is not significant even to have a correlation.
Mm-hmm.
So that's the big thing, meaning that, first of all, your perplexity cannot be used for evaluation because that's not reliable. The
Mm-hmm.
second, that you're training for very ineffective objective that don't guarantee that give you this improvement on the long context benchmarks.
Mm-hmm.
That I think that's implied this two things. And so what people usually do is accurate more data, accurate better data, accurate better benchmark to measure this gain and to improve the data. But we actually think maybe there's a way that you don't need to do this whole human curation, but you actually can fix this perplexity matter.
Mm-hmm.
So I can still do nectar prediction,
Mm-hmm.
but I can recover this correlation between the nectar prediction and the long context benchmarks. So
Mm-hmm.
what we really find that um, the long context performance of the models only correlate with the perplexity on a few K tokens
Mm-hmm.
of the original data.
Mm-hmm.
That's also kind of intuitive. For example, when I see a word, most of my word I'm saying that is just depend on the last word I just said. It's very
Mm-hmm.
short context dependent. But when I say, okay, my paper actually requires my long-term memory over, my past experience, and whether I can see these few tokens right reflects whether my model can do long context.
Mm-hmm.
But that's actually very sparsely scattered in the context. If you just do, nectar prediction over all the, tokens, you're
Mm-hmm.
diluting your training signals and
Mm-hmm.
diluting your evaluation signals.
Mm-hmm.
On long context. That's why you don't have the good correlation with the benchmarks.
Mm-hmm.
So what we do is that we find a very kind of smart, but still very simple mechanism to really find this K tokens,
Mm-hmm.
all the natural corpus, and you find that after you find this K token, you can have a perfect, like a very significant correlation with the benchmark score, more than like 0.9 Pearson correlation.
Mm-hmm.
And then when you use this new mechanism to fulfill training your model, only emphasizing these K tokens, you get a huge boost of the on the long contact benchmark. Like we get like 22% on long eval, like 11% on ruler. This are like a baseline message.
Mm-hmm.
And I think there are actually some follow-up works using our method to train their hybrid models. These are models that try to hybrid, linear attention models with transformer attention, summax attention.
Mm-hmm.
So their model is more limited in their memory. And they actually found that for training this hybrid model, you have to use our method can give you 30% gains.
Mm-hmm.
Because I think that also illustrates you have to focus on the really important things to your training if your model is not that capable.
Mm-hmm.
So I think I think another lesson of sparsity is different from the first lesson. You can have activate a few dimensions, but not about your training. You also should train your models with the important sparse signals.
Mm-hmm.
Uh,
Awesome. Well, thanks for giving us a great overview of this paper. Do you want to maybe talk a little bit about, briefly, like some of the other papers that you've had? Like, for example, ICML 2025 this year was actually very successful for you. You had three papers that were accepted. Of course, we already talked about one of the papers at the very beginning that was given an oral award. But for instance, I think you had another paper titled On the Emergence of Position Bias in Transformers. And then you had some other papers as well. Do you want to maybe give us a brief overview of some of the other papers that you had?
Oh, sure. So I think, yeah, maybe I can talk about the emergence of position bias in
Mm-hmm.
transformers. I think that's also a long-standing problem that were observed in transformers. So
Mm-hmm.
in transformer, we use uh, causal mask to,
Mm-hmm.
to let the model do all the graphic generation,
Mm-hmm.
and we use lots of position encodings. And so the outcome that LLMs we are actually having do have this various form of position bias.
Mm-hmm.
That's actually pretty annoying. That if you put your important things, the things that we want to retrieve at the beginning of the prompt, at the middle of the prompt, at the end of the prompt, the model behaves dramatically different.
Mm-hmm.
Can have more than 20% difference in
Mm-hmm.
the performance. Even they are independent. Even in some scenarios, they are not really, dependent on where the position is, and people have so many different techniques to extend, how I can use longer context with
Mm-hmm.
less position bias, or uh, okay, how I can try to get rid of it.
Mm-hmm.
But there's lacks I think a more fundamental understanding of why this transformer have this position bias. So what's the original of it? There are so many, like loss in the middle is one of them. That models like is bad at retrieval something in the middle.
Mm-hmm.
Also attention sink, where the models have a huge attention over the first few tokens.
Mm-hmm.
Yeah, I think all sorts of these problems. So I think the difficulty in this understanding, there are so many factors,
Mm-hmm.
the confounding factors. First of all, your data, like your training data, you train with human data. Human data, people believe that they already have a partition bias. We try to put important things in the beginning and try to put important things in the end.
Mm-hmm.
And last important thing in the middle, people say, oh, maybe they just, inherit the partition bias of human data.
Mm-hmm.
Or you have a different position bias, like loop position embedding, that you kind of emphasize the recency bias into the model.
Mm-hmm.
That you try to focus on the nearby tokens during the generation.
Mm-hmm.
Yeah. So there are I also have the transformer that have a causal mask that
Mm-hmm.
also introduce some potential bias. There's so many confounding factors. So
Mm-hmm.
I think the first thing we do in this paper is try to isolate these factors.
Mm-hmm.
We do experiments ensure that there's no data bias. All the
Mm-hmm.
data are independent,
Mm-hmm.
put in the comment, and we also get rid of the potential bias.
Mm-hmm.
Let's say there's no influence of the position bias. We
Mm-hmm.
still observe the models have some dramatic position bias. That
Mm-hmm.
is favor something, especially in the beginning of the sentence.
Mm-hmm.
That's very similar to attention sink, but we still don't understand. That's definitely attribute to transformer, and you cannot blame the data or blame the position coding
Mm-hmm.
for that.
Mm-hmm.
So we do observe that actually you can have a rigorous theoretical understanding of that. Then actually you can use a graph understanding of it, because transformers, many people actually see that. Uh, Different tokens are like different nodes, and
Mm-hmm.
by doing attention, you're constructing a graph
Mm-hmm.
among all these nodes, and there is information flowing from each node to the other node, and this graph structure actually determines your information flow through the transformer. So
Mm-hmm.
that actually what we use for our analysis. That
Mm-hmm.
you can show that this transformer, when you have the causal mask during the generation, this graph is super imbalanced,
Mm-hmm.
in the sense that this first few tokens, they are the context for all the other future tokens.
Mm-hmm.
So they are super important. The influence will be accumulated through this longer and longer context,
Mm-hmm.
and through deeper and deeper layers. So actually, we can theoretically prove that if you have an infinite number of layers, your attention will only attend to the first token, the first only token in the model. So actually, that's exactly what attention sink is observing in the model. Yeah,
Mm-hmm.
so I think that kind of explains what is the source of the transformer architecture, potential bias. It's actually because this causal mask structure that you
Mm-hmm.
create an imbalanced graph. Imagine that you don't have this causal mask, then your nodes are equivariant, like they are super, equal.
Mm-hmm.
Then you definitely don't have any attention. If you use diffusion models, that will actually, our theory just implies there will not be such
Mm-hmm.
bias. But now if you actually have the causal mask, it actually give you this bias.
Mm-hmm.
Yeah, I think that's the main takeaway. But under this framework, you also formally categorize what's the interplay between this causal mask and my partition encoding,
Mm-hmm.
and all sorts of this, interactions.
Mm-hmm.
Yeah, so I think also kind of point out to how we can actually have some model, get rid of this particular bias,
Mm-hmm.
because we actually show, maybe design the causal mask in this way, you actually always emphasize in the beginning tokens. You have the partition encoding emphasize the last tokens
Mm-hmm.
that creates the loss in the middle.
Mm-hmm.
So if you have a better design of either the causal mask or of the partition encoding, that you can, lift this to a more uniform attention distribution, that actually could solve the problem.
Mm-hmm.
But I think that's for future work,
Yeah.
more to explore. Yeah, and I think I really like that work. It also kind of featured by MIT News. I think the why pick us is also because it's kind of give a theoretical, a more principal understanding of why
Mm-hmm.
this model has this problem. Before we get to solve it, we actually need to have some understanding of it. It's not about
Mm-hmm.
more about theory because in deep neural network you can't have very rigorous theory, but more about how I can have a very clear understanding of what the root cause of these problems.
Mm-hmm.
Uh, yeah,
Okay, awesome. Thank you for giving us so much information. So
yeah,
maybe before we end the podcast, we can ask you
mhm,
some questions about
yeah,
your thoughts on the field as a whole. So I'd say
mhm,
broadly there are four main categories that your research has gone under.
mhm,
Contextual understanding and reasoning, self-supervised learning, robust deep learning, and structural deep learning. And I also know
mhm.
that one of your sort of research philosophies is that the theory side is very important. In other words, like nothing is more intuitive than a good theory. You want to maybe talk to us briefly about how you've been
Mhm.
able to build a deep theoretical understanding across these four different research categories, and maybe do you have some advice for researchers in these categories?
Yeah, um, I think that's kind of the flavor I'm trying to
Mm-hmm.
build into the current, development. I think people are very swift, at this
Yeah.
moment about
Yeah.
developing different variants of these models. But
Mm-hmm.
I think what's actually very important is to keep this message very simple,
Mm-hmm.
because academia can do all sorts of research, but sometimes it make it difficult. Actually, very hard for industry to
Mm-hmm.
deploy. I think what industry value is something actually is very simple.
Mm-hmm.
It's very easy to understand. Actually, it's really solve the pain. I think to actually have this kind of innovation, I think also similar to what we do in sparse autoencoder and
Mm-hmm.
this kind of, is actually you have the better understanding of what's the core problem of this models, the carbon masters. I think in order to really understand that, you sometimes it's actually very helpful
Mm-hmm.
for you to have it's kind of like you put a stress test to your own self. Like,
Yeah.
can I really clarify
Mm-hmm.
what's the follow this model? Like,
Mm-hmm.
why transformer have a position bias? You
Mm-hmm.
have so many big intuition, like what I said, people, opinions, but when you actually do some ablation studies on this, when you
Mm-hmm.
actually pinpoint what's the problem, actually you're much closer to a real solution that
Mm-hmm.
actually very simple, but actually fix the problem.
Mm-hmm.
Um, yeah, I think that would be my advice to future research. Also, kind
Mm-hmm.
of a guideline I try to follow in my research. Try
Mm-hmm.
to build, very simple and fundamental and generalizable solutions.
Mm-hmm.
And yeah, I think at this stage it's actually not hard to publish a paper because everybody can
Mm-hmm.
publish a paper. It's more
Right.
about how I can publish a paper that will actually be interesting for real practitioners.
Mm-hmm.
Yeah, I'm also surprised that actually many people from the practitioners have also gotten interest in my, like the theoretical understanding of transformers
Right.
because they actually really care about this problem.
Yeah.
Why they're a position bias? People actually from the series had didn't told them before.
Yeah.
Yeah, I think that's I think the community I really values in this time. Yeah.
Mm-hmm. Awesome. And I guess maybe one last question. Across all the different research areas that you've worked on, is there maybe a specific research topic that you're very excited to work on in the near future? I mean, obviously you've worked
Mhm,
on, since 2023 and even maybe before that, you had
mhm,
work in, learning with symmetry and Laplacian kind of Laplacian things, and you've had work across the board. There's so many different
yeah.
papers across so many different areas. Now we have Yifei Wang in 2025 in the summer of 2025. What is the current Yifei Wang really excited to pursue?
Yeah, I think there are two things.
Yeah.
I think we'll try to push forward at this time.
Yeah.
Um, I think there are kind of also directions. I think
Mm-hmm.
they'll have huge potential. I think the first is actually the sparsity thing I
Mm-hmm.
talk about in this podcast. Like,
Mm-hmm.
uh, I think what more very exciting that actually sparsity already delivers so much gains. Like,
Mm-hmm.
you have the MOE sparsity, like a knowledge
Mm-hmm.
sparsity that actually push this frontier forward. You also have the context sparsity, like the
Mm-hmm.
sparse attention to give these models. And I think the two dimensions that I mentioned in this talk, actually some two new dimensions. Like you can have a sparse and importance weighted training mechanism
Mm-hmm.
to emphasize the key topic. Actually, can shoot your models to tackle these challenging problems
Mm-hmm.
that really care about few tokens. They also have a sparse repetition method that can you allow your model to work with sparse repetition that's much more efficient than the previous method. I think that actually, you know, it can bend the scaling curve. I think
Mm-hmm.
to I think notable
Mm-hmm.
amount of there. I think that's for but more about how I can make this current models better, more capable. I think the other dimension also try to explore alternative training methods. Because
Mm-hmm.
I worked on satisfied learning before. I still believe in satisfied learning. I think current methodologies like ROVR, they're super good.
Mm-hmm.
But actually, rely on or source of verifiers. Sometimes it's really hard to build that. And it's not scalable. It's not really as scalable as next token prediction
Mm-hmm.
as they use for pre-training. That's how we build GPT. But I think for the current paradigm, it seems that there have to be another GPT moment to actually you can very reliably human effortlessly scale that to a huge number of tasks that we can actually encounter in practice.
Mm-hmm.
That's also something I'm very excited about in this direction.
Mm-hmm.
Yeah.
All right, awesome. Well, thank you so much for coming on the podcast. We really appreciate it.
Yeah. Thank you so much for having me.